Welcome to this talk about physical unclonable functions and how they contribute to the security of RISC-V cores. We expect RISC-V based processors to be featured in upcoming applications where tailoring the CPU to the application brings a major benefit in terms of energy efficiency, real-time capability, or safety and security. RISC-V cores will likely be controlling drones, collaborative robots, or autonomous vehicles, and RISC-V will also be a candidate for electronics in critical infrastructure like power plants. There you want to have as much insight into the inner working of your devices as possible in order to guarantee safety and security. While safety means dealing with the random hardware faults, security is a bit more diverse. Security usually includes the three aspects of confidentiality, integrity, and authenticity. Confidentiality is about your government not being able to eavesdrop on your private phone calls. Integrity in this picture is about being certain that your phone hasn't been tampered with to install some lawful interception circuitry. And finally, authenticity means you know that you are actually talking to whom you expected to call. A common acronym for these aspects is CIA. Sometimes reliability and availability are also considered part of secure and trustworthy systems. Availability in particular has become a major concern since technology providers have monopolized the processor IP market and since geopolitics is interfering with economy. Anyways, the extended acronym isn't as catchy anymore. There are a couple of important building blocks for ensuring security in a RISC-V processor. You should be able to calculate encryption, decryption, and checksums at some reasonable speed, even on small devices, so there should be hardware to support these algorithms. Most of the algorithms rely on some form of random numbers, which, in order to pass well-known quality tests, should come from a truly random source, called an entropy source. This could, for example, be a circuit that converts the thermal noise into bit streams. Raw bits from an entropy source first need to be preconditioned in order to fulfill certain statistical properties. These conditioning circuitry might be part of the entropy source as well. A trusted execution environment in its whole ensures that you can run code that has access to sensitive data, for example, the random data generated by your entropy source, without other processes being able to interfere, and in general with very strict access control. This includes secure boot mechanisms, which make sure your firmware hasn't been tampered with, and secure update protocols, which, for example, check the origin of firmware updates. But a trusted execution environment can also include all kinds of special register sets or even fully isolated auxiliary cores, which only run security subroutines. The last step is to harden all of these components against so-called side channel attacks, like differential power analysis or purposeful fault injection. These countermeasures include masking to reduce the correlation, for example, between repeatedly processed plaintext data and the measured power consumption, and hiding techniques to overlay these side channels with noise in order to make it harder to find the useful information. An initiative to bring all these bits and pieces together is the OpenTitan project. OpenTitan tries to develop a RISC-V based so-called secure element. That means a RISC-V core of reduced complexity that holds to higher security standards and can be integrated into other designs or systems as a trusted component. You might want to check out the OpenTitan documentation online or come back in September when we will have a talk about OpenTitan. You might also have heard about the upcoming Cryptographic Isa Extension. This extension mainly supports the performance of cryptographic algorithms by defining specialized instructions for popular ciphers and hashes. but it also describes a standard interface to access randomness generated by an entropy source. And it deals with a certain type of attacks based on runtime differences by providing operations with data-independent execution times. Other parts of a security architecture are, for example, described in the physical memory protection specification. And eventually, the RISC-V Security Working Group will be publishing an architecture-level definition of security measures like ARM did in the past with its platform security architecture. All of the aforementioned techniques are meant to ensure integrity and confidentiality, but for identification purposes alone, they are sometimes too expensive to implement. Identity information is often required to detect counterfeit parts or parts from overproduction that are sold through gray channels. Simple and cost-efficient solutions include logic locking techniques, where the netlist sent to the manufacturer is modified to only produce correct behavior if a secret key is applied to some of the inputs during startup. Other solutions even rely on placing small ROMs with unique identifiers on the manufactured PCBs, or embed RFID chips right into the boards. One of the oldest techniques has also been revitalized and applied to dies, engraving in individual laser marking into the back of the die. We develop a low-cost solution for the identification of RISC-V chips based on so-called Physical Unclonable Functions, or PUFs. The basic idea is that although fabricated chips are basically identical, very much like one egg is to the other, on a closer look, small random differences become visible, caused by the production process. PUFs make these imperfections measurable and utilize them to derive random but stable data. Luckily, physical modifications to the die, like reverse engineering methods, will likely change these imperfections and thereby corrupt the PUF's data, which can be easily detected. PUFs are hence useful to provide unique identifiers for trusted identification and, with some additional effort, to provide seed values for random number generators.
For semiconductor-integrated physical unclonable functions, the very small variations in the manufacturing process are used as a random source. These variations can be divided into global and local variations. Global variations can be categorized into die-to-die, wafer-to-wafer, or lot-to-lot variations. They contain some random portion, but also very much likely have systematic differences. Local variations of devices with much smaller distance can be predominantly seen as random and can therefore be used as an entropy source for device authentication or key generation. These random variations are mainly determined by the matching parameters of the integrated components, like transistors, resistors, or capacitors. Many PUF designs using semiconductor variations have already been implemented. Some examples are shown on the left-hand side of the diagram. They use intrinsic device variations that don't need an external impulse or programming to have a unique behavior. One of the earliest examples is the SRAM PUF, where each cell consists of 6 transistors. When VDD is powered up, the threshold voltages of the individual transistors differ, caused by process variations, and force the cell to generate a memory value that is either 1 or 0. This value seems random, but stays stable when powering the device multiple times. With n memory cells, only n bits of output can be produced. In reality, it's even less because not all cells are stable enough. Hence, this is also called a weak PUF. Ring oscillators can also be used to get a random output. The oscillation frequency differs from one to another, and a pair of 2 oscillators can be used to produce 1 bit of PUF output by deciding which one of them is faster. For security reasons, every oscillator can only be used once, and therefore only n divided by 2 bits can be generated with n oscillator cells. An example for a parameterizable PUF is the arbiter PUF, where propagation delay of two competing signal paths is measured by a so-called arbiter. The signal path is binary alterable, and therefore 2 to the power of n bits can be generated with n delay stages. Because of the exponential growth of output or response bits with the number of elements, the arbiter PUF is considered a so-called strong PUF. As said before, we want to perform authentication in small embedded systems with the help of PUF. These systems are usually designed with low-cost devices, and therefore the overhead for the PUF should have a small implementation size. The idea now is to take components which are already present in the integrated circuit and reuse them for the PUF application. We're considering a typical measurement application where you have some sensor and actuator, but also analog and digital signal processing. Between the analog and the digital world, we always use some kind of analog to digital or digital to analog converters. These are often constructed as an array and therefore offer many individual components to be used as a random source. We are now taking a passive charge sharing DAC or DAC as a component stock for our PUF. It consists of an array of binary weighted capacitors. The functioning principle of the DAC is as follows. The capacitors in the middle, which are called reference capacitors, will be pre-charged to a certain voltage, VRP minus VRN, and then consecutively added into the network. With every inserted capacitor, a voltage step at the output, P minus M, occurs. Depending on the scaling factor beta, the voltage step is dependent on the order or permutation of the set stages. Most nonlinearity occurs if we have a very small beta, meaning a small reference capacitor in comparison to the other capacitors in the stage. Because we can decide which permutation to use, we can use n factorial possibilities to actuate the PUF, which are called challenges. So the number of available challenges is 3 factorial in this example here, which equals 6. For an 8-stage PUF, which we have integrated later, factorial 8 or 40,320 challenges are available. The PUF operation can be divided into 4 phases, which are the reset phase, where the reference capacitors are pre-charged, the decoding phase, where the binary challenge is converted into an actual permutation, the output set phase, where the reference capacitors are added and the voltage steps occur, and the ADC conversion, where the analog PUF response is converted to a digital word, which then can be used for the ID generation, for example. We integrated the PUF core together with our iRISC processor, which follows the 32-bit RISC-V instruction set with the extensions I, M, A, F, and C. The processor can be clocked up to 200 MHz in the chosen 180 nanometers technology and performs about 3 core mark per megahertz. It has a built-in standard periphery like UART, GPIO, and timers, and features many core capability. FreeRTOS and SL4 are also supported to make real-time applications or formal verification possible. On the left-hand side, you can see the final chip layout with the RISC-V controller at the top and the ADC and PUF core at the bottom. We used an additional dedicated PUF core to be able to change the capacitor sizes to our needs for an 8-stage array, which you can see in the middle. On the right-hand side, you can see a chip photo, where you can also see the SRAM parts, which are placed onto the RISC-V core. During the next month, we will be implementing the signal processing logic to precondition the raw PUF data. Thereby, we will implement an interface that is compatible with the Cryptographic Isa Extension. Because our PUF produces a random value for each input parameter, so-called challenge, we'll test its performance as a seed generator for TRNGs. In the future, we'll work on the stability of the PUF and on error correction mechanisms, so it can be used as a secure key storage element and in challenge response-based protocols for authentication. The presented work is done in the IGF project Sichel in cooperation with the University of Applied Sciences Offenburg and funded by the German Federal Ministry of Economic Affairs and Energy.